Okay. Hello, everyone. My name is Daniel Casellas. I am the Scientific Director at Eurecat, and it's a pleasure to welcome you all to this industrial workshop about advanced material characterization methods to face the new challenges in the sheet metal sector. Today we will see the results of 3 different R&D projects: the ToughSteel, the Crystal, and the MIPRE project. These projects have received funding from the European Union through the program of the Research Fund for Current Steel. And these projects, let's see if it works. Okay, these projects mainly addresses the mechanical performance of high-strength steels, because high-strength steels are the main materials applied in lightweight construction of vehicles currently, and it could be in the future. We see that the high-strength steels is the perfect choice for lightweight because they combine outstanding properties with high levels of sustainability and affordability. And regarding sustainability is a topic that we are all interested today. Just to mention that the CO2 footprint in steel production is one of the lowest in the materials for lightweight, and also steel has a lot of possibilities in recycling. So we're going to see in the coming years projects and results about development of newer steels with a higher degree of recycled material and of course lower impact in the footprint. So what we're going to see today, this is the agenda. We will start with in the morning session about the fracture toughness to address the cracking resistance of high-strength steel. This is the result of the ToughSteel project. In the afternoon, we have 2 sessions. The first one is the Crystal results, the Crystal project, about enhancing the risk or reducing the risk for the hydrogen environment in high-strength steels. And we close the session in the afternoon with the results of the MIPRE project about advanced models for predicting mechanical properties in press-hardened steels. We will have three stops, 3 different 1 coffee break, 2 coffee breaks, and 1 lunch break. It's excellent opportunities for networking. So please, once that you are here in the Eurecat facilities, use it for networking. Contact our speakers, our colleagues, and discuss things. This is the most interesting thing of this in situ meeting. About the logistics. We all know how it works nowadays in this online meeting. So for those of you that are online, please remember to write your questions in the Teams chat, and don't forget to mention the speaker to address the question and which is the question you would like to address. And if you experience any technical issues, so contact the email you see here in the slide. For those that are here on site, the conventional way, raise your hands and address the question properly. We can just start with the presentation of the ToughSteel project. I would like to introduce the moderator of this session. Is Davide Frómeta. Davide Frómeta is PhD in material science. He did the PhD in the fracture mechanics application to solve edge cracking and address crashworthiness issues in high-strength steels. He's currently the director of the mechanical behavior of metals here at the Eurecat. So David will be the moderator of the next session. So please, David.
Okay, thank you very much, Daniel, for the introduction. Also, first of all, I would like to thank you all for participating in this event, especially to the speakers. So also for their positive feedback and willingness to participate and share with us also their experience in this ToughSteel project. So as Daniel said, I will be moderating this session 1, which is called Fracture Toughness to Address the Cracking Resistance of High-Strength Steels, which is related to this ToughSteel project. And during this session, we will have also the opportunity to share some of the experiences with the industry that we have in this that we had in this project. Some results from the open call, this collaboration, because we have different representatives from different industrial sectors. We have participants from SSAB Forvia, Benteler, SEAT as well, also MW from Italy, also colleagues from the University of Luleå and so on. So we'll have the opportunity to see some of the main results and the application of this fracture toughness approach on how to use these new criteria, these new characterization criteria to understand different failure phenomena in high-strength steels. Then, well, I will start this session with a short introduction to the ToughSteel project to understand a little bit why are we here, what was the aim or the motivation of the project and what is its ambition. So let me start with by the beginning. This is the general presentation of the overview of the project. The ToughSteel, which is called Dissemination and Valorisation of Fracture Toughness as a Material Property to Rationalize Crack-Related Problems in Advanced High-Strength Steels. The acronym, as you know, is ToughSteel. This is an European project funded under the frame of the Research Fund for Coal and Steel, the RFCS. This is as the title says, is a dissemination project, so it's not a research project itself, but it consists on the dissemination of the results gathered or gained in different or previous research works. The project had a duration of 2 years, so it started the 1st of July of 2021, and it ends next Friday, the 30th of June. So they've been 2 exciting years of intensive work and a lot of dissemination events, workshops, webinars. So probably you have seen a lot of our activities all over these 2 years. So the consortium, some information about the consortium. The consortium is formed, I don't know, anyway. It's formed by 8 partners. So the project is coordinated by Eurecat. And also we have the collaboration of the participation of the 2 universities, the Catholic University of Louvain, also the University of Technology in Luleå, also 3 steel associations, Eurecat from Sweden, UNESIT from Spain, and also Associazione Italiana di Metallurgia from Italy. Of course, the collaboration of CRF from the Stellantis group, and also the national Spanish standardization body, UNE. Okay, now let's go to what are the objective of this ToughSteel project. Well, here the objective, as I said, is a dissemination project. So the main objective is to spread the word, to disseminate the results or the knowledge gained in previous projects about the implementation of new fracture criteria. So based on this fracture mechanics testing, to understand different cracking problems when dealing with applications of high-strength steels, high-performance steels, to solve problems related to, or crack-related problems that can be related to the forming or in service performance. Also today, during the different presentations, also we will have the opportunity to see different examples of how this works and how we can use these different fracture criteria to understand different failure phenomena, to define different quality control criteria, etc., in order to improve the material design and selection. So our claims that the project is expected to contribute to improve the efficiency and competitiveness of the sheet metal forming process involving this high-strength steel application, because we think that the knowledge that we can gain with using or applying this kind of methodologies can help also to prevent production losses, also related normally to material specifications, and also to reduce the time to market of new materials, for example, when designing on and validating new materials design. So I put here, I summarize more or less some highlights of the project. So the main activities that we have been doing during these 2 years. The first one is the creation of a fracture toughness database. This is here, our colleagues of the University of Louvain, they made an excellent job here. So here the idea was to try to gather all the information that we had, that we can find in the literature, in research works, PhD thesis, etc., about the plane stress fracture toughness of thin metal sheets, because, well, some years ago it was really difficult to find information about the fracture toughness of this property, especially in thin ductile sheets, thin metal sheets. But fortunately, in the last years, this has changed a lot. So there's plenty of literature about that. There's a lot of information. So there's a sign of the growing interest especially in both the academia and the industry on this kind of properties to better understand the performance of these kind of materials. So what we did here, it was the exercise of compiling and gathering all this information together in a fracture toughness database. So you can, of course, here in our website, you can have more information about it on how to access. So this is it's open access, so you can access anytime you want. We only have to follow a very simple registration step, and then you can consult data or even encode data if you want to update also this database. So you will find relevant information about the different materials, complex phase steels, all kind of steels, and also the relevant information about chemical composition, microstructure, elastoplastic properties, fracture toughness values, etc. So this is a perfect tool, for example, for positioning your products in the case of industrial partners, also for research purposes, for writing articles, etc. And this is a good database to where to find this kind of information. Also, one of the main outputs of this project was this elaboration of the user guidelines. Okay, this is an official document. Again, also in our website, you can find and download also for free this document. So we created this document. So as the name said, it's a kind of guidelines, where we provide some definitions, recommendations, etc. About the application of this fracture toughness approach on explain different methodologies to better understand how to measure fracture toughness and in the plane stress fracture toughness of ductile metal sheets, different methodologies on their application, the definition of the different fracture toughness parameters, and also after that how to apply these fracture toughness results or these fracture toughness values all over the value chain of the high strength steel production, from the material design, so for microstructural design, for example, also for material selection, quality control, and also including even different successful case studies with previous collaborations from previous projects that show how to implement this kind of or this new fracture criteria to understand different fracture problems or cracking related phenomena. Of course, as I said, this is a dissemination project, so the core activities were focused on the dissemination. So we organized a lot of training webinars, academic and industrial workshops, with the idea was also to promote this discussion, and the engagement of both the academia and the industry. So I think in that sense, the project has been a complete success. So of course, an example is the representation that we have today here from the industry and the interest generated all over these 2 years. So regarding the training webinars, we have organized a total of 5 online training webinars, so dealing with different topics on how to apply these different fracture toughness concepts to understand different phenomena like forming, crashworthiness, material selection, etc. Again, also all this information, all the webinars were recorded and the videos and everything is available in our website. So if you are interested in take a deeper look at that, feel free to follow us on our website and you will find everything there. Also, as I was saying, the different academic and industrial workshops, like the one that we are celebrating today. So this is a kind of a special one because it's not only an industrial workshop, but also we will share also the experience that we have in the open call that I will explain a little bit more in the next slides. And also as a final result, we will also have by the end of the project 2 digital courses. We will be prepared by the University of Luleå, where, the aim is also to provide or to make more available all this information about the fracture toughness, etc. Regarding the contribution that's our contribution to research, we prepared a total of 4 scientific publications during the ToughSteel project. We have different topics about how to different aspects to be considered in the evaluation of the essential work of fracture when applied the methodology to high strength steels. For example, the optimization of the essential work of fracture for the characterization of metallic sheets, also how to apply this fracture toughness to optimize, for example, a thick press hardened parts, and also a more, let's say, more industry oriented, how this influence of toughness of fracture toughness properties on real components, on automotive stamped components. Also, well, apart from that, so we have also one paper in preparation, again, which will be basically like a kind of a complete, comprehensive review of this essential work of fracture and different applications, etc. Okay, now also one of the other of the key results or outputs of this project is this the celebration of this open call. Okay, which is so this open call that was launched during the last year by October. So we during the month of October we opened this period. Well, the companies had the opportunity to apply, to present their case studies and also try to implement this new fracture toughness approach or these new methodologies that we are proposing to understand and also trying to solve at least the problems, the day-to-day problems related to cracking, fracture problems during forming, etc. So from the applications, we selected a total of 6 case studies. So here the ones that, of course, were awarded with this open call. We have SSAB, of course, what I mentioned before, more the participant that we have today here, SSAB, Forvia, MA. Unfortunately for MA, we didn't have time to prepare a proper case study, but of course there's something that we will keep in mind for future collaboration with them. MW Italy, Benteler Vigo, and Marcegaglia. Also Marcegaglia was not available to come here today, but our later Laura will share our experience with their case study. Okay, regarding standardization activities, also here we have some important information to mention. Apart from the previous the 10 workshop agreement that we performed in previous projects with the idea not to standardize these new methodologies, or not new, but new when applying to high-strength metal sheets. We developed this test method for determination of the essential work of fracture of thin ductile metal sheets. And now in the frame of ToughSteel, we created, also of course with the collaboration of UNE, this 10 workshop, which the title Fracture Toughness Evaluation Methodologies Apply to Advanced High-Strength Steel Sheets. And in the frame of this workshop, we created these 2 documents, these 2 10 workshop agreements. The first one related to the user guidelines that I showed in the previous slide. It is called Guidelines for the Evaluation of the Plane Stress Fracture Toughness of Advanced High-Strength Steel Sheets in the Frame of Fracture Mechanics. Again, as I mentioned before, related some guidelines, recommendations about the different methodologies, the meaning of different parameters, how to apply for these kind of materials. And the second one, which is the test method for the determination of a cracking resistance index for advanced high-strength steel sheets, which is also closely related to this essential work of fracture methodology. But now we were thinking here to provide something even simpler, a really simple test that can provide a first estimation of the cracking resistance of these high-strength steel materials. So here the idea was to provide some kind of index that helps also for material selection, for material screening in a very fast way. So these 2 workshops agreements haven't been published yet, but they will be available really soon, on the 5th of July, and they will be free, so available in this in the Centenelec download area. Finally, as I was saying, also we'll have all this information that I have shown here. All the information we have been updating, all the website, also the projects, all the information regarding webinars, scientific publications, the deliverables, the fracture toughness at the base, etc. You can find all the information in our website. Okay, that was all from my side for the first introduction. Now I think we have a short video, an animated video that we prepared for the project, so if we can share it.
During cold forming has become one of the greatest fears of high-strength sheet metal producers and part makers. This risk is even more accentuated with the emergence of new advanced high-strength steels, whose greater cracking susceptibility requires the development of new fracture criteria able to predict crack formation and propagation. Recent findings have shown that fracture toughness is a reliable property to assess edge cracking and crashworthiness in a simpler and faster way. ToughSteel aims to disseminate the industrial, economic and environmental benefits of measuring fracture toughness and boost the usage of this material property to understand crack-related problems. The project provides practical tools, including a user guideline for fracture toughness evaluation in thin sheets, along with an open access fracture toughness database, and other resources such as training webinars and industrial and academic workshops. Our main objective is to upskill the industrial community to optimize material selection, prevent production losses, and reduce the time to market of sheet metal products. We estimate that the implementation of these approaches will result in a reduction of up to 25% of scrap metal and failed parts, and 20% of greenhouse gas emissions due to the cuts to machinery usage time. Fracture toughness is key to increasing the competitiveness of the European metal industry. Learn how to measure it and optimize your business operations at toughsteel.eu.
Okay, well, I hope you liked the video we prepared for the project, and I hope you can see it also from home. And well, I think that was also my first introductory part. I think it was a fast one. I think we are a little in the schedule, but okay, I think we can move now to the important stuff. And now I think I can introduce our first speaker of the session, which is Vili Kesti. Mr. Vili is a senior specialist in the Knowledge Service Center of SSAB Europe. Mr. Kesti's career has been focused on the research and development of new high-strength steel grades, along with providing technical support to SSAB customers for their specific forming processes. So he has been an employee at SSAB since 2010 and holds a Master of Science in Mechanical Engineering with a major in Physical Metallurgy, and currently, this is, as I said, this is Senior Forming Specialist at SSAB Knowledge Service Center. He will be presenting today the presentation with the title Blanking Behavior of Hot Rolled Steels, Correlation with Fracture Toughness Properties, which is also, as I mentioned, one of the case studies that we had in this ToughSteel Open Call. So please, Vili, and the floor is yours.
Thank you, David, for a really kind introduction. And so my name is Vili Kesti. I'm working as a senior specialist for SSAB Europe. And today I will be talking about hot rolled steels, fracture toughness, and also some blanking properties. Of course, I will take this opportunity to talk about our company shortly in the first part of the presentation. Then we will go through our case study in ToughSteel project. And of course, I will summarize everything at the last slide. So we are a steel producing company based in the Nordics. We have steel mills in Finland, Sweden, and also in Americas. As you can see, we have quite a long steel-making history, and we are operating all over the world. Over 50 countries we have employees. And you can see also our yearly production, which is about 9 million tons. And if we are looking at the global steel market, we are quite a small player. As you can see, only 3% of the market share. But if we go into our focus areas, special steels, now I'm meaning quench and tempered hot rolled steel grades, we are actually a market leader in the world, so we have about 25% of market share there. We are growing also in automotive industry, and we have a really strong position in our home markets in the Nordics and in Americas. So we could say that we are a rather small company, but we are actually leader when it comes to high-strength advanced steels, especially in hot-rolled grades. And last but not least, We are aiming to be the first fossil-free steel company in the world, so really making a big change when it comes to producing steel. I'm not going into this in details. It would take most likely the whole day. So you can find more information in our website, and you will see some interesting pictures here and there in the presentation also related to this topic. But I think we should go into our case study, and we selected 5 different hot-rolled materials. They are in 3 millimeter thickness, and the idea was that we will select very similar strength levels for all the materials, but very different microstructures in order to make things really interesting. The testing plan, of course, normal mechanical testing. I will show you also the base microstructures of these steel crates. We conducted also the ISO hole expansion tests, and here at the Eurecat also these essential work of fracture tests. Now we will present results with the fatigue pre-cracks, and hopefully in the future we have also results for the notched specimens. And then I will also show you some results on shearing, punching, and fine blanking tests for 2 of the materials. And here you can already see one of the fossil-free things. That's the waste that we are creating with the new technology. It's water, not CO2 anymore. Here you can see now the mechanical properties of these steels. As you can see, we got a really good set of materials. A, B, C, and E materials are almost identical when it comes to strength values. So we have eliminated the factor coming from the pure strength of the material. Material D is having 100 megapascal more strength, but we could say that it's still on the same ballpark to these other materials. And you can see also SEM pictures of the base microstructure here. You can see that steel A is quite a pure ferrite, polygonal ferrite. Then we have also really complex phase steel as a B. Including, let's say, bainitic ferrite and MA islands. And then C is again based on a ferritic microstructure, not so polygonal anymore, maybe a little bit more quasi-polygonal ferrite there. Then D is, let's say, mix of all salads. I'm not even trying to tell that what you are going to see there, because there is almost everything, starting from ferrite, bainite, quasi-polygonal ferrite, martensite, everything. So it's a really complex phase steel. And steel E, again, based on ferritic microstructure, again, a little bit different morphology there, but we could say that A, C, and E are ferritic steels, and B and D, those are clearly complex phase steels. Then starting the results from hole expansion, and actually you can see that we have 2 different levels of results. 3 of the materials are on a, let's say, normal level of these hot-rolled steel crates above 700 megapascal yield. They are normally around 40% of hole expansion results. But 2 of the steels are showing really high levels of hole expansion ratios, over 100%. And actually this is creating now interesting variation of these materials, even though the normal mechanical properties are looking almost the same. Then some results from the essential work of fracture. if you have more questions related to this, I think Laura can help. The thing here is that if we look at the essential work of fracture values, again, we have two different levels. Let's say the low level is around 200, and the high level is above 5, even 600. So really distinctive differences between these materials. And we could see also that when it comes to plastic work, there is only one material that is statistically different to the others, and that's the steel E. And now one interesting question is of course that what about the hole expansion ratio and essential work of fracture? Are we able to correlate these? Here you can see the results from these 5 materials. And before going into this, I would like to bring Mr. Frómeta's previous work, published work, including much more results for different kind of materials. And you have found a really nice correlation for the materials, essential work of fracture and hole expansion ratio. And now I took all these results from a previous publication, and you can see now the small dots in our figure on the left. And actually what we can see is that those old results, the new results, are actually aligning really nicely. We can actually see the correlation there. But the steel B is creating something that we don't understand, and that's the question mark there, that what is going on. We have double checked, we have made more tests, and everything is as it's shown here. So meaning that that steel grade is creating much higher fracture toughness than we could expect from the hole expansion results. So there is something to further research and try to understand. Then more results on these essential work of fracture tests. So here we have also results for the true thickness strains. And what we can see here, again, 2 different levels of results. These are aligning really well with the essential work of fracture results, that the 3 high-level materials with the fracture toughness are also showing really high true thickness strains in these specimens. And one thing that I want to highlight here is also, if you are looking at the fracture surfaces, now I'm using the laser only, most likely not in teams visible, but steel A, we can see severe delamination, steel C, the same story, and steel E, quite a severe delamination. But it doesn't seem to affect on fracture toughness or these true thickness strains, because steel A is on a really low level in both, but the other 2 laminated are on a really high level of results. And again, something maybe we don't fully understand yet. Then some results on punching, shearing, and fine blanking. We selected 2 materials, steel A and steel B. As you can see, really identical mechanical properties when it comes to strength, rather similar hole expansion ratios, but now we have 2 different levels of essential work of fracture. And steel A, punched hole, you can see the surface is not really nice. And we have also the shearing results with the different cutting clearances here. You can see that the fracture surface is not looking really nice after cutting. But steel B is showing almost perfect cut edge in all these cases. It's not sensitive for the cutting clearance, for example. And actually, the only thing that we could say that this material B is showing much higher level of essential work of fracture. Of course, we have only 2 steel grades here. Is it a universal truth? But really interesting results. Then fine blanking. this is a special design that we have, including different tooth radiuses, different cutting angles, and we are using zero cutting clearance in a fine blanking, and we are monitoring that do we see any cracks, defects on the fine blanked cutted surface. And again, the same steel grades, and maybe you can already guess the kind of results and story. Steel A is showing defects on these fine blanked surfaces. I wouldn't recommend this grade for fine blanking purposes, but steel B, we couldn't find any defects, even with the most challenging tooth radiuses. So it's absolutely perfect for this application. And again, the thing that is differentiating these materials is essential work of fracture. Then I think we have time to summarize. We made successful tests for hot rolled grades now in 3 millimeter, also these fracture toughness tests. We could see really clear differences between these materials, two really different levels, and we could rank the materials according to these results. We could see that there is a really good agreement on essential work of fracture and the fracture surface strains, through thickness strains, a really good correlation there. And we found out that the ferritic grades are showing delamination, but it's not actually affecting that much on these results because we have steel A is on a low level and the other two are on a very high level with the lamination. And also we've tried, of course, the previously published correlation from Mr. Frómeta, that is the whole expansion ratio and essential work of fracture are really correlating. And we could say that, yes, there is a correlation, but there is the one material that is behaving or not behaving. Let's say there is something going on, and we have to look at that more closely. And there is also good agreement with these essential work of fracture results and our shearing and fine blanking results with the two materials. Most likely we have to look more materials and see that is this universal truth. Personally, I think we have a lot of things and questions open when it comes to the effect of microstructure on these essential work of fracture results, how different microstructures are affecting the results. We don't understand everything yet there. And I want to finalize my presentation with the future. And here actually you can see the first fossil-free steel vehicle in the world. It's produced by hydrogen-reduced sponge iron, so it has been emitting water during the steel production, and it's up and running, and that's the future, hopefully sooner than later in a big scale. Thank you.
Well, thank you very much, Vili, for the very interesting presentation and the interesting results. I agree with you. There's a lot of open topics to get a further look at it. Now, well, I think I take the opportunity to remember what, but after. Yeah, okay. Now I take the opportunity to remember that we will have, after the next presentation, we will have a time slot for question and answers. So please write in the chat. If you, those who are participating remotely, you can write in the chat your questions. And now here also from the audience, if you have any questions, you can also raise your hand when it's that time. Okay, now we can move to the next presenter, which is Valerie Woimbee from Woimbee from Forvia Faurecia. She's a scientific expert processing technologies. She's been an expert in materials since 2011 in Forvia, and she has scientific expertise in processing technology since 2022. She will be presenting also the work called Unexpected Cracking at Forvia, so first experimentation of essential worker fracture, expectations to enrich Forvia simulations. So please.
So good morning, everybody, and thank you to Eurecat for the invitation. It's a very lovely opportunity today. So I'm going to discuss about our industrial case regarding the unexpected cracking at Forvia. So we had the opportunity to be a participant to the open call, and also after that we launched thinking internally to see what we can do with those results. So this is the topic of the presentation. I will introduce quickly the Forvia group. I will show also the context of the fracture development inside Forvia, our case quickly. After, the result will be introduced by Laura. And after, I will come back to in fact launch some idea and thinking about what are our expectations. So quickly for the new group, resulting of a merging last year with the German ELA. In fact, we have the seating. I belong to the seating. I'm located in France. We have the interior system, the clean mobility, the electronics, also the lighting coming from ELA, and the life cycle solution. In fact, in that, we have also electronic monitoring for the future of autonomous driving and also interventional intelligence for the environment recognitions. So quickly, we have 6 business groups, 150,000 people around the world, worldwide, in China, in North America, in Europe. Although Europe is 30% of our activities. So we are at the 7th place for the ranking regarding the automotive sub-supplier. And just quickly, we have also the first to launch a net zero by 2045. It's really important, and we have signed a contract with SSAB to provide green steel at the horizon of 2025-26. So the context of fracture development, why fracture knowledge is a must. First, there are the formability, in stamping, fine blanking. And so we have this type of part. It's a component for the seat. And assembled on the seat, we have to, in fact, predict the crashworthiness behavior. And there are very high level of accelerations. So the presentation of our case. No, sorry. Yes. The context of fracture development. Yes, formability, fine blanking, the crashworthiness. Sorry, I'm going back on the road. So, and also this is an example of modeling with different plastic criteria. We have different tools, in fact. Some are very well known, like Autoform or LS Dyna, Hypermesh. And we are based mainly for the forming limit on the forming limit curve to predict the final behavior of our parts. But that's not enough. That's why we have, for instance, different production centers. Is one supplier production center in Portugal called Bamesa. They have received, in fact, they are purchasing some batches around Europe. And there are some cases where 20% of the world production is affected by those cracks without knowing why. Because when we investigate the material certificate, all is the same. In fact, we have the certificate for the cracks material and for the material which doesn't lead to crack. And regarding chemical composition and mechanical characteristic, it's the same. And even with the examination of the microstructure, it's quite impossible to predict that one material would lead to cracks and the other no cracks. So that's, in fact, the importance to have another mean to investigate the behavior of material, and the essential work of fracture, in fact, was the great opportunity to do it. Separate the materials regarding the essential work of fracture results. And it's really significant and really significant for us. And in fact, this has been introduced to the simulation groups inside Forvia, in Germany, in France, blah, blah, blah. And because, in fact, currently, we are only examining the global formability. In fact, we are launching a lot of ToughSteel tests. We have the many properties for the different batches, of course, the elongation, blah, blah, blah. But regarding the local formability, and this is the example of this, sorry, yes, no, sorry, no, okay. Yes, yes. The global, in fact, yes. Yeah. The cursor, oh, I can't see. Yes, and so the local formability can only be, in fact, investigated by such testing samples. And it's really an important result to get, in fact, the stress under local, in fact, concentration. Currently, the forming limit curve, in fact, there are some studies that have already launched. For instance, there are articles from Daimler that show, in fact, the minimum of the forming limit curve here, in fact, just give a correlation with the global formability. It's important for the deep drawing, but for the fine blanking, and of course, if you are doing a hole, it's not correlated. That's why we have this whole expansion ratio currently in-house. It gives important and also consistent data regarding this behavior, but it's not easy to set this type of test, and because there are dependence on the machining of the hole, and you have a result which is not really material intrinsic. So even if David and Al also, Frómeta, show that there is a good correlation with all expansion ratio and the essential work of fracture, but I think there is something more, because this is a graph coming also from Daimler that shows the scattering, the large scattering of the whole expansion ratio. And also, even in Germany, we have also different contact with the material supplier. There is a trend to drop this to drop this methodology because it's not enough consistent for the advanced strength steel, where we are looking for accurate results. So my questioning, in fact, is the essential work of fracture measurement could, in fact, bring something really important for the future of development and even for our simulation. This is an example of our Gizmo methodology of simulation to predict the crash behavior. But we are missing this type of, in fact, of samples. And when we investigate with my colleague of the simulation team, they are not able to tell me that there is a prediction of this type of cutting-edge failure with our current simulation. So there is something to do. I think there is something to develop. And because this is really simple and is very not expensive at all, considering for this type of test, it costs a lot, in fact, for the company, and it takes time. There is really something to exploit for this methodology. And so my conclusion is to say the essential work of fracture method may replace the whole expansion ratio test for its accuracy and simplicity to set up, to predict, for the prediction of crack during forming or crash. And we will be able, in fact, to sort advanced high-strength steel according to their cutting-edge sensitivity. That means that the material lab also could have this type of test in their daily task. and because we have a quick experimental and consistent value for built-in simulation models. So that's my presentation of my opinion regarding the methodology and our experience in Forvia.
Okay. Thank you very much, Valerie. Now you have the spoiler of the results, maybe. But as we did the test, I think we can show them, and you will see the actual results and how we performed the test for the essential work of fracture. Okay, I think they are preparing the presentation. So here for this case study, as Valerie already explained, we tested, or they selected 3 DP steels, okay, with similar mechanical properties in all of them, only that they had problems. One material presented here cracks, 2 materials presented cracks during cold forming, and one was not presenting any cracks in this process. Then, as we were saying, we applied the essential work of fracture methodology. So let me just briefly introduce it. You probably already know what it consists of, because if you have been following this project, you may have seen already this method. But basically, it consists of the idea that with this method we can separate the energetic contribution of crack propagation into terms. One is the essential work of fracture energy that is related to the energy needed to create 2 new cracks in a material. And the other part is the plastic work, which is related to the deformation around the crack propagation. Okay, to do this test, we need samples of the geometry shown in the presentation, which are dense specimens, double-edged notch tension, which have 2 cracks, 2 symmetrical cracks, and then these specimens are tested at tensile test. The particularity of these specimens is that they have to present very sharp notches. And here we perform the test with fatigue pre-cracks notches. Then we perform the test of these specimens, and we obtain these load displacement curves, where we can calculate the area of this curve, which is the work of fracture. And if we need, then we need to do it for different ligament length to separate these 2 contributions, these energetic contributions. And when we perform all these different tests for the ligament length, we can escalate this work of fracture and make a regression, which you can see in the slide. The intercept of this regression is the essential work of fracture value, which is this interesting result for cracking resistance. And also we can get the slope, which is this non-essential plastic work. Here we can see the test conditions we used to perform the test, which we used fatigue pre-crack specimens, about 10 specimens for each material, and the ligament length from 8 to 16 millimeters. Okay. Next on, we can see the results that we got from these 3 materials that we tested. And we can already see some huge differences between the material with presenting no cracks in the forming processes, which is material, the first one we can see. And then we can find lower fracture behavior for the other 2 materials that presented cracks during forming. This is an interesting result because here in the bottom we can see the comparison between the mechanical properties of these materials, which were almost the same for all 3 materials. However, the fracture toughness results were presenting this differentiating result, and it was coincident with the results that they were finding in their performance of forming. Okay, so it's I think a parameter that can easily relate these edge cracking problems that sometimes cannot be predicted with the mechanical properties. Finally, we also performed these measurements of the true thickness strain, as we already saw before with the SSAB case study, that the correlation between the essential work of fracture values and these measurements was good. In this case, we can see also that the correlation between the fracture toughness is similar for the three materials. The one with presenting no cracks in the forming, it presents the highest true thickness strains values. Finally, with just some brief conclusions that already Valerie said, that we can see a clear differentiation on fracture toughness between these three materials from different batches, but the same mechanical properties. It can be a good indicator to predict edge fracture during forming, and also it can be an additional parameter included in the typical mechanical properties used, and true thickness strain presenting a good correlation in this for fracture toughness. Okay, so thank you very much.
Okay, thank you, Laura, for presenting the results. Sorry I didn't introduce you before, but Laura is a researcher at the Mechanical Behaviour research line here at the unit of metallic and ceramic materials. Well, as you have seen, she's currently performing and managing all this fracture toughness and essential work of fracture test here at Eurecat. She's currently also studying the Master of Science in Material Science and Engineering at the Universitat Politècnica de Catalunya. Well, thank you again, Laura. Thank you again to the speakers for the interesting presentations. Now, before the coffee break, we have some time for questions and answers. And now I would like to invite also the speakers to join me here in the table. Please, Vili and Valerie, if you want, you can come here. Okay, now we have some time. I don't know. First, we can start maybe, I don't know, from the audience. There's any question here? Yeah.
Hi, good morning. Santiago Oliver from UNICEF, the Spanish Steel Association. As I used to do, I would like to know a bit more about that, some specifics, let's say, steel grade that doesn't perform as it was expected. Do you have any idea what could be the reasons for such a deviation in the expected result?
Yeah, it's a really good question, and unfortunately, I don't have a really good answer for that. But I think the microstructure that we are seeing in that material is, let's say, it's something that we usually don't see. It's not the normal CB structure. It's not the DP structure. And let's say the ferritic base there is looking much different than, for example, normal DP steels with really high hardness MA islands and then ferritic base. I think most likely this microstructure is something that we don't understand yet completely. But it's a good question. We just have to learn more.
Yes, Santiago, interesting point for the steelmaker to see if I understand what is happening. It's at the end, small things has a big impact on properties. Really, maybe I'm just speculating. The material that is less tough. Did you said that it's they have more martensite islands, or have you checked if there's a difference in the distribution of martensite or ruthenian austenite compared to the material that behaves well?
Actually, this really complex phase grade was actually creating high values, and the low values were with the pure ferrite, little elongated ferrite, I would say, and the other one was this mix of all salads, which was also higher in strength, and so those two ones were on a lower level. So most likely the first one is related to the basic ferritic microstructure, maybe elongated one. And the other one is most likely due to the fact that it's having even too complex steel base, also including martensite there.
Yeah, what we saw, and David worked a lot in this, is that the finer and more homogeneous microstructure, the better for the toughness. So maybe also at sub-grain level, maybe we have more fine structure in the ones. But I agree with you, this is something that we have to go in more in detail. And about the material, was the material B is the one that is not following the whole expansion, and you mentioned that maybe the material is wrong, but maybe what is wrong is the whole expansion ratio test. What do you think? Because Valerie gives some insight about that.
Yeah, exactly. I think now the whole expansion test itself is not the best one to characterize these materials. But it's a little bit strange that this material is showing really good edge quality, almost perfect, and it's showing really high fracture toughness, but still only 40% of whole expansion ratio.
maybe if you increase the clearance, the cutting clearance, maybe you have better results. Because probably the whole expansion is based on ISO, that ISO standards request a 12% clearance. Maybe increasing the clearance, we see better results.
During the years, we have also tested a big variety of different cutting clearances, and it's not making it much better. It's almost the same level.
Okay, it's another explanation then.
And so I have a question. When you are producing, in fact, during the current production, can you predict the result in advance? Do you know, in fact, how much percentage of steel will be with all expansion test above 100 and the percentage below? And you are going to sort with your customer, with your supplier, sorry? With your customer, sorry.
Yeah. Usually for these really high whole expansion test or value grades, we are also making production testing. So we are validating the whole expansion ratios before we are sending those to customers. So we are kind of testing the whole expansion ratios.
But is it running consistently? In fact, with time, do you have stable results?
With those grades, I would say that which have over 100%, those are quite a stable products. But I know that there are also products that have a much bigger scatter in the results. But yeah.
Okay, thank you.
Okay, thank you for the presentation. It's Silvia Molos from Eurecat. And it's a question for Vili. Have you considered to study the effect of hydrogen in terms of hydrogen embrittlement of these new fossil-free steels?
Yes, there is a huge amount of different research initiatives going on actually at the moment regarding both scrap-based steel production, which is most likely closer, and also this hydrogen reduction sponge iron with the completely new metallurgy. We have a huge amount of research going on. Of course, because it will be a really big change, and we really have to look all properties. But so far, the let's say hydrogen reduced sponge iron, the first trials that we have with those raw materials are showing actually better results. So with the DRI, we are even able to make more pure steel.
Hi, I'm coming back to the same question. I have a certain passion about outliers. I love outliers. Maybe just a thought. Maybe somehow this kind of, let's say, very complex structure could create a much more, let's say, divergence in very local point when performing the test. Maybe it could be corrected by a statistical approach. I don't know how many tests do you carry out for each single value, but maybe when the structure becomes very complicated with very lot of specimens in the crystallography, in the metallography of the steel, maybe then you could somehow correct it by doing, instead of 3, 4, 5 tests, 10 or something like that. Just try to capture a bit of such a complexity that is not easy to assess in lower specimen testing.
Yeah, I fully agree that the more complex the microstructure, the more statistics we would need in order to make really good conclusions. And I think the complex structures are creating also, let's say, more or less stochastic behavior of different things. So I would really love to see the, let's say, bigger amount of tests and statistics that can we see also difference there. But according to these tests, actually these were creating really good R-square values within the test set. So the materials were behaving even surprisingly well in the tests and similar results.
Yes, maybe I can add. Yeah, with this, I think with these results or the test that we have performed or that we perform with the essential work of fracture, we have seen in previous projects or cases that we will show later as well in the next presentations, that it's easy to find or to localize this small differentiation in the microstructure sometimes, or small defects and so on. It's easy to detect with the amount of specimen we usually test during this methodology. So I think this is also a good method to characterize this specific localization of different properties of the material. So.
Well, I am Miguel Dourado from Benteler Vigo. I have a question for Vili also. In my case, when I have quality problems with materials, most of the cases, the tensile strength, elongation, yield point on the coils are intolerance. Yeah? But when we test the material with ToughSteel results, we can see quite different behavior in the material. So are you planning in the future to add to your certificates tests done with ToughSteel methodology or something similar?
Again, really good question. And actually, yesterday we were talking about that here during the lab visit also with the test method. Actually, I'm not saying that you can find it from SSAB certificate. I'm not promising that and doing that at the moment. But I have to say that this method is really well suited for industrial testing because it's fast, especially with the notched cracks or the notches. It's a really fast test that we could implement in the industry. And I know that there is this standardization work is also going on. And I think we need more results, really see how different materials are behaving, the scatter behavior statistics. And if we can see that it's a really good kind of property to solve and test also during the production, why not? But usually these things, if we are making something like 500,000 tensile tests in the production in order to add 500,000 EVF tests. It's not really simple, but I think it's a promising because many times, let's say, academical tests are really scientific, labor-taking, time-consuming, and those are not really easy to implement into the production facilities. But I think this has the potential to be a really good test there.
Okay, I have one also in the same line, also, but now it's a question for Valerie. So what do you think are what do you think are the next steps to implement something, new fracture criteria like the essential work of fracture, for example, at your plan or in modeling and so on? What do you think are the next steps?
Yes, in fact, there is a work that has been given to my colleague of the simulation teams to work, in fact, to a way to predict the edge cracking, and so I have expectation regarding their investigations, and another way I would like also ask to Material Lab if they were ready to invest for such, in fact, testing equipment, because we are in fact blocked because the analysis in the Material Lab are only on global visions, and more because there are more advanced high-strength steel in our portfolio. The lab analysis are really without any additional, in fact, value comparing to the material certificate provided by the supplier. So I think internally we have to make some prospective investigation to enrich our lab analysis, and also take the opportunity of the lab analysis to integrate in the simulation modeling. It's really important because we are really at a turn, in fact, in terms of simulation, because the money invested in the model are so huge. The only way now to become more economic performant is to reduce the cost of the testing and the cost of the simulation. And so the time spent for running, in fact, the model are really incredible. And even my colleagues of the simulation are not really aware on the way to take advantage of the results. They are not able to take the theory to the reality of the part. And so I think we have to integrate such quick, simple tests and to really advance quicker. And the pressure is at a level that we are, in fact, investigating modeling, in fact, in India with artificial intelligence, blah, 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 because we are looking for a different way to get rid of the situation. It's really high pressure on the testing cost and simulation cost, in fact. And with 70% of reproducibility and even 80%, it's not enough. We have to predict 90%. It's the objective for the next year. So I think we are ready to see outside. Thank you.
Thank you. Thank you very much, Valerie. Now we have received also some questions from the audience online. The first one is directed also to Vili. So what is the role of string hardening during tensile testing on fracture toughness and correlations? String hardening influences strain localization. Do you like the simple questions? Yes.
Yeah. So during the fraction mechanics tensile test.
Yeah, I guess they're maybe looking for the correlation between the strain hardening and fracture toughness. I think maybe we can add something with this on that.
It's a good point. We haven't checked that, so I think it's a good comment, and we should look into that.
Yeah. We actually have done it, especially in these multi-phase advanced high-strength steels. So what we found is there's generally the trend is an inverse correlation between strain hardening and fracture toughness, especially in these multi-phase materials with let's say that the formation mechanisms were, for example, in dual phase. When you compare a dual phase like a steel or a complex phase, more homogeneous microstructures, usually the mechanisms that contribute to improve string hardening, also have a negative effect on crack propagation, on very local formability. So usually the trend, what we have found, it's a negative correlation. But of course, the more material you test, and also the more challenging it is to establish any kind of correlations. But I could say it's something.
Yeah, I have a comment to add because your article, in fact, my colleague from Forming Expertise, he had forwarded me the article last week, and he said it's completely the opposite I have observed on my experience. Mm-hmm. So I told him, I gave him a reply because he was expecting a reply from my side as an expert. And I told him it's because the solicitation mode are quite really different. Okay. And because you are soliciting in the plane, in the plane, stress planes, it's completely different because it's more complicated, in fact. And we have to take care of that. So it's experimental from my forming expert colleague.
Thank you. Okay, I think we have a couple more. This is more, no, I have another one here. Same strength level, different microstructure. What is the, I guess, hydrogen embrittlement susceptibility? This is the question to Vili again.
Yeah, I'm a forming specialist, so I have to get that question to my hydrogen specialists. With these two steels, for example, here, I think we have test results, but I have to admit that I don't know. I'm not the hydrogen embrittlement expert, but we have those also within SSAB. So
maybe for the next PhD, you have also an interesting topic to start.
Yeah.
Okay, and then two other rapid questions. Maybe they are maybe for Laura regarding the experimental evaluation of the essential work of fracture. How long does it take for fatigue pre-crack preparation? And also the ligament length is defined between the fatigue pre-cracks or between EVM notches.
Okay, thank you. Well, the first simple one, the fatigue, the ligament length of the fatigue, well, of the specimens are determined after the propagation of the fatigue cracks. Okay, and the first question was how long it takes to prepare one specimen. Usually for one specimen with fatigue pre-cracks, it can take an hour. So for 10 specimens that it's usually normal, 10 hours, it would be maybe 2 days of propagation for one material, probably. Okay.
Can you comment with share ones?
Yes, yeah. We will present also the other...
You like spoilers, I know.
Yeah. You are asking me? I was reserving for later, but no. No.
It's okay.
Okay.
We see after the
break.
After the break, okay. We'll see a faster method later. Okay.
Okay, then. Well, I think thank you very much. Thank you, Marina. Thank you all very much for your participation. I think with this we can close this first part of the session 1. Then we have a 30-minute break, and so we'll be back in 30 minutes at time. At 10:50? No. 11:20. Yeah. Thank you. See you.
11:20.
Now, without further ado, let me introduce our first speaker of the second part, which is Miguel Dourado from Benteler. He's the production unit leader in the hot and cold stamping department in Benteler. He's been in Benteler for more than 17 years, and he's a professional with a wide experience in the automotive industry. And he will be presenting now the work or the presentation with the title Identification of Material Parameters to Prevent Formability Issues in Strip Steels. So please, Miguel.
Hello, everybody. Thank you for attending this workshop. As David says, my name is Miguel Dourado. I am the production unit leader. I've been working in Metals for 17 years. At the beginning, I was the production planner, and after that, I was production unit leader first from laser cutting, then from hot stamping, and now hot and cold stamping. Well, Benteler in 84 words. Benteler develops solutions that makes the difference for our customers, employees, and society. We are passionate about producing safety-relevant products, services, and systems for the energy, automotive, engineering sectors that lead to success. And we do that in close proximity and collaboration with our customers. With our technological expertise and strong focus on successful implementation, we keep our promises. At Benteler, we give our all with courage, ambition, and respect, but we never give up. Benteler, the family of driving professionals since 1876. This is my plant, Vigo plant. Well, there are only 26,000 square meters. Maybe for many of you, this could be a high surface, but believe me, for us, it's only few square meters. We are approx 430 employees. Our main products are chassis products, 59% of share, structural products, hot forming parts, IP support bumper, 40%, and only 1% cold stamping products for chassis and structure. David, este está apagado. Gracias. Okay, these are some examples: rear axle, pillars. Our customers, main customer for Vigo is Stellantis, 70%. Also, we supply parts for VW, 11%, for Ford, 10%, Volvo, 9%. And as you can see, from Vigo, we have a logistic problem because we have to send the parts quite long. So we have to fight with the cost, with the logistics team to have more share in the market. Some brief description of our problems. The parts are manufactured with 3x100 material, and it cracks during the stamping process. The cracks always occur in the same radius of the part. The part is produced in cold stamping process. The thickness is 1.76 millimeters, and it has 10 microns electrogalvanizing coating. Main specifications, well, are that, but I guess it's not too much important. The material is delivered in coils with 1,120 millimeters width. Coils are cut into blanks with the geometry shown in the image. One stroke produces 2 blanks, and the area where the crack occurs will be marked in red in all the image. Blanks are stored maximum for 2 days before stamping. As I said, we made 2 processes. First, we cut the blanks from the coil, and after that, we have to stamp them in another press. Blanks are stamped in a transfer tool, and one stroke produces 1 part in the stamping process. The cracks always appear in the same area and operation of the stamping process. The length and number of cracks per coil varies for no apparent reason, and several tests have been performed to double-check properties of the material, I mean our requested tolerances, but nothing out of the ordinary has been found. This is a graphic to check if there is some relation between the number of cracked parts and any of the chemical components of the coil. But without going deeply, honestly, we can't find if the problem is percentage of carbon or, I don't know, any other chemical component. It's, the problem is totally random. Some technical improvements that we have done at the beginning, we had to implement an additional knife in the blanking tool to eliminate the sharp edge of the coil. And the edge of the coil could cause a crack start. Also, we had to apply a coating in the die of the tool. All that green color is the new coating. The coating reduced the stress and tension in the critical area. And also, we had to smooth the radius in the critical area, because a smoother radius reduces the stress and tension in the critical area. Obviously, we can't go to any kind of radius because the quality of the customer put the limits here. Okay. Our targets to achieve with ToughSteel open coil, well, to find the root cause of random cracks. We don't know if the problem is the material specifications, the aging of the material, or other. To improve the quality status of this part, of course, to reduce the euros of scrap cost, and, if possible, transversalize possible solutions to other products. We have tested 3 different coils. One of them, it was a coil with very high scrap rate, and the other 2 were coils with 0 scrap in the Vigo production. And as you can see here, the behavior is quite different. The coil okay is in black color, and the coil 1 and 3 that were okay in white and gray color. Also, quite different results in essential work of fracture and plastic work. Quite different. But the certificate of the coils were okay. Tensile strength and all of those kind of parameters that the supplier attached to the coil. Conclusions. The study has shown that a coil with a high rate of cracks has a very different mechanical properties than a coil that doesn't generate defects. In this case, the test which has been performed to double-check properties of the material requested tolerance has shown also difference with the certificate attached to the coil. And unfortunately for me, we still don't know what's the root cause to have a high number of cracks. I don't know if the problem is the chemical components or loss of properties due to aging or other possible causes. And that's all.
Thank you very much, Miguel, for your presentation. Thank you for accepting the invitation to share and for sharing with us also your experience in this ToughSteel open call. Well, now, let me remember that as we did in the first part, we will have also a questions and answers session by the end of this part before lunch. So please, the questions you can write your questions in the chat, and we will read by the end of this session. Then now I think it's time to move to the next presenter. The next one is Davide Ronco from the Research and Development Manager in MW Italy. He has been involved for more than 9 years in the design of steel wheels for many customers, and during these years he developed several new methodologies of FEM analysis to simulate the tests required for validate steel wheels, also with a special focus on materials and experimental simulation correlation. So please, Davide, the floor is yours.
Good morning to everybody. Thank you, David, for the presentation. Okay, I will start. my presentation. Okay. Starting from a really fast summary on what we will see in this presentation, we will have an overview on the steel wheel and a focus on the fact that the steel wheel is a safety component, and consequently we need to predict the fatigue behavior. Then the activities we did with David and the team about the link between the fatigue and material characteristics, and then the conclusion. Okay, the steel wheel overview. So there are several types of wheel with different material and different technology. There are several, as you can see here in this graph, there is the laser here. Okay, there are different material. Some of them are really expensive. The steel wheel are here, so are the cheaper one. And our direct competitor is the casted aluminum wheel. Here in this graph, we can see the comparison between the steel wheel and the casted alloy wheel. The casted alloy wheel is the blue one, that is really good for the aesthetics. It's really good for the rigidity because it's a massive component, but not so good, for example, for the CO2 footprint and for the cost and the weight. If we look at the standard steel wheel, so the wheel with all the hole around, we can see that okay, for the aesthetic it's not so good, but it's really good for the weight. It's really good for the CO2 footprint and for the cost, and not so much for the rigidity because it's thinner and it's not a massive component. Then we have a third solution that is a steel style wheel that is like this. This is done in steel. It's not it's similar to alloy, but it is steel. And this is a good compromise between the two typology of wheel. Okay, how is produced the steel wheel? The steel wheel is composed by two components: the disc, this is the central part, and the rim. Both are done starting from the coil. From the coil, we cut the blank. And then the disc is done by a stamping process, and the rim is done by a rolling process. Then the disc and the rim are fit together, are assembled and welded. After there is the painting, the quality control, and then the packaging and shipment. Okay, the wheel is a safety component. The wheel is a mature component. Is together with the fire, is one of the first invention of the the man. The geometry and the technology are already established, and as I said before, is a safety component. For that reason, it's difficult to innovate. It's difficult to improve, and this type of product, because it's already strongly optimized. Considering that the wheel is a safety component, the main aspect for the dimensioning of the wheel is the fatigue, because the wheel have to sustain the weight of the car, and there are several forces that play on the wheel. There is the radial forces coming from the ground, there is the lateral forces when we make the corner, the pressure, and so on. For that reason, there are different tests for fatigue. The main two are the bending test, the rotary bending test, in which we fix the wheel in a special machine with an arm. This arm is going in rotation and apply to the wheel a bending moment. This test is stress more the disc, so the central part. And the two parameters for the test are the bending moment itself and the number of cycles that the wheel should reach. The second test is the rim rolling test, in which we put the tire on the wheel, and we push the wheel against the drum and go in rotation. In the test, we can apply only radial forces, or if we introduce a relative angle between the axis of the wheel and the axis of the drum, we can also introduce an axial forces in order to simulate the behavior of the wheel in the corner. Then also in this case, we have the pressure, because we have the tire, and the number of cycles. In this graph, there is an example of what is required by the customer. Sometimes, usually the customer requires 1 or 2 levels of loads. Here is loads, generically loads, but it can be bending moment or Newton meter or radial forces in Newton, and gives a minimum number of cycles to respect. The test is okay when the wheel overpass this minimum number of cycles. Here there is an example on the crack after the test on the disc with the dye penetrant. And this is an example of the crack on the rim after the rim rolling test. So, for that reason, the wheel that is composed by 2 different parts, 2 different components, have different needs. For example, the disc, the material for the disc, should have high performance on fatigue, high cold formability or stampability, and typically the material that we use for the disc is DP600 grade, with a range of thickness between 2.8 to 6.4 millimeter. Regarding the rim, it should have a high performance on fatigue, high weldability, high cold rollability, and in this case the grade are low alloy steel from S235J2 to S460MC. And the thickness range is lower than the disc, is between 1.10 to 4 millimeter. It depends from the load, for the type of vehicle, and so on. So, considering that the fatigue is the main aspect for the steel wheel, and considering that this type of product is not suitable for fast prototyping, because when we create the tooling for produce the wheel, it should be definitive. So we need to predict the fatigue behavior at the beginning of the wheel. And we have several instruments for the prediction. The first, for sure, is the phase simulation, in which this is mainly used in the phase of optimizing the RFQ phases. The pro is that it's very fast and reliable. The contra is that when we have to, considering that the FEM is correlated to experimental data, if we don't have experimental data, for example, new material, new process, this correlation is less reliable. For that reason, we have this type of test. This is the second instrument. It is test on a specimen, in which we bending the flat specimen in the bend specimen, we can introduce the hardening phenomena during the stamping, and we can convert the pure traction and compression forces in the bending forces, similar to what happened in the bending test. The pro is that the test on specimen is well representative of the test on the wheel, and does not require the wheel manufacturing, so we can do before to create the wheel. The contra is this type of test has only one failure mode, is always the same, in the same position, and is dedicated to the material, not to entire component that is composed by 2 different components with the welding and so on. Then there is a third potential method, that is the method that we are developing during the study, that is the link between the material characteristics and the fatigue. The pro is that is an objective judgment, so we have a number and we correlate it with another number. The contra are that we need the calibration, and the process of the stamping is not included in that type of link. So just to very fast how it look the rotary bending test correlation. As you can see here, there is in a typical simulation the stressed area that corresponds exactly where we have the crack. The same for the rim rolling test simulation, in which we apply the loads, the distribution of the loads, and so on. And the FEM detects that the critical area is this, and in fact the crack is here. Then this, the test on specimen is the test that we did in the Fatigue for Light project that has the scope to reduce the weight of the car of 15%. So in that case, we tested a new material. As I said before, the material for the disc usually is DP600. We try to go in a complex phase X800 with the scope to reduce the thickness and so consequently the weight of the wheel. If we compare the results in a Wöhler graph with a flat specimen, we looked at the CP800 is very good comparing to DP600. But if we bend, this difference is not so much evident. But if we make the shot peening after the bending, again the CP800 improve a lot, and it is really better than the DP600. Here we have just a superimposition between DP600 and CP800 before and after the shot peening. You can see in orange we have the DP600. There is not so much different between before and after shot peening, but there is a huge difference on the CP800 after the shot peening. And so this can permit to reduce the thickness of the wheel of a lot. For sure, in the bent specimen, we have just one failure mode. In the wheel, we have more failure modes, so this 1.1 millimeter is not exactly what we have in the wheel, but we can reduce a lot. And the first test that we did on the wheel confirm, and not on the bent specimen, but on real test, confirm this tendency. Okay, the last point is the link between fatigue and material characteristics. So this is activity that we did with Eurecat. So we identify one case study, one wheel. With the disc is done in DP600. We identify 2 different suppliers of steel and 2 batch for each supplier. So in total, we have 4 different type of the same wheel. We produce the wheel with these 4 type of steel, and we send the blank to Eurecat. MW made the test on fatigue, and Eurecat analyzed the fracture toughness. Okay, this is the fatigue results. As is visible, there is a difference between the 4 samples, especially between so steel supplier A and steel supplier B. There is not so much difference between the 2 different batches. But these discs are done with the same material grade. So, and this is a problem because for the simulation, this is not predictable. So we have just the same material weight for the same material grade for the simulation, but we see that there is a difference. So here we have just only the focus on high load and low load, and is visible the 2 level. No, material A is a little bit better, much better than material B, the same. So what can be the reason of this difference? We make like a sort of Ishikawa analysis, and we make some questions. So it can be a different process? No, because the wheels are done in the same times, in the same press, in the same batch. Different failure mode? No, also in this case we analyze all the wheels tested and they have all the same failure mode. Different test condition? No, also this, no, because the operator is the same, the test conditions are exactly the same on the same bending machine with the new screw and so on, so the tests are really identical. Some possible defect on samples, we check the samples and we didn't see any visible defects. So small difference of thickness. So the coil sometimes have some tolerance in the thickness. We analyze the thickness, and there is a difference, but it not explain the difference on the fatigue, because if you remember, material A was better than material B, but in that case the thickness is not. It doesn't explain this behavior. So different material characteristics. Okay, probably this is the answer. And so this is the activity that we did with Eurecat. Here we have the essential work of fracture, comparing with the fatigue in orange. For each high load and low load, we have the fatigue for material A1, A2, B1, B2, and also the plastic work. And it's visible that there is a quite good correlation between the number of cycles and the essential work of fracture at initiation, so the gray bar. Then we analyze also other characteristics coming from the material certificate, like yield stress, UTS, the ratio between yield stress and UTS, and the elongation. And okay, there is also in this case quite a good correlation between the elongation, and there is also a small correlation in this ratio, except for the material A2. So are needed it can be interesting to extend this study to other parameters and with other case study. So concluding, we observed a significant difference between two different steel suppliers with the same material grade. The difference is mostly due to the steel characteristics. And this difference is not predictable by the FEM simulation if we consider as the same steel grade. And we found quite a good correlation between the essential work of fracture at the initiation and the fatigue. The analysis of these characteristics can be an instrument that can help to predict the behavior on fatigue. We observed this. And we would like to extend the study to other failure mode, other cases, like, for example, the crack starting from the ventilation hole. This can be really interesting to compare with the essential work of fracture. And can be also interesting to include in this analysis also other parameters like yield stress, UTS, and elongation. Thank you.
Okay, thank you very much, Davide, for also your interesting presentation and for showing with us this interesting case study. Now we can move forward to the next presentation, and let's see a little bit more about this relationship between fatigue behavior and fracture toughness. And the next presentation is called Understanding the Fatigue Notch Sensitivity of High-Strength Steels Through Fracture Toughness. This will be a shared presentation by Sergi Parareda and Michele Tedesco. Sergi is a researcher at the unit of metallic and ceramic materials of Eurecat. He's a PhD candidate in material science, and he has been involved in research and development projects since 2015, and is mainly focused on fatigue and fracture behavior of metallic materials. On the other hand, we have Michele Tedesco. He's the global responsible for metals and anti-corrosion. Michele started his career in CRF, in the Central Research Fiat, in 2013 as a sheet metal specialist. And in 2022, he became the global responsible of metals for Stellantis. He is also advisor, the OEM board member of Automotive Circle and International Automotive Body Congress, and he is coordinator of several Stellantis projects and CRF reference for international research projects. So please, Sergi, you can start your presentation. Thank you.
Thank you, David, for the introduction. Yes, today we will present another approach, or how we can use the fracture toughness values instead of predicting the edge cracking, using them to predict the fatigue behavior of materials with some defects. So, as you probably know, the main tendency in the automotive industry is move to the internal combustion engines to the electric vehicles. So this change of platform results in an increase of weight of the vehicle in about 15 or 40% of the vehicle. So if we want to maintain the original weight of the vehicle and reduce this weight of the electric vehicle, what we can do is reduce the weight of the chassis of the vehicle. Okay, so by reducing the weight of these different components in about 24 to 30%, we can reduce and maintain the original weight of the vehicle. In fact, this is the aim of the Fatigue for Light project, where we are developing new techniques and also using new materials to reduce this weight of the vehicle. In this case, we are considering, as I mentioned, different materials from advanced high-strength steels, stainless steels, aluminum alloys, hybrid materials. So we are considering almost all the industrial materials, let's say, to reduce the weight of the vehicle, but also considering the affordability and sustainability of these materials, which is an important part in the design of these components. So this is a project carried out by 13 partners, where we have research centers, academics, and also part producers, so the final producers, and steel making and also material making partners to address this or to achieve this aim. So, but when we are talking about chassis components, we have to address different properties. So in this case, here you can see two different chassis components, a lower control arm, and also the chassis of the heavy-duty vehicle. And if we want to reduce the weight of these components, we need materials with good fatigue properties, but also with a good formability. Since we are decreasing the thickness of the material, we have to maintain the stiffness of the component. So this stiffness reduction can be compensated by changing the shape or slightly changing the shape of the component. So we need a good formability. So here, the banana plot, if we want to improve this behavior, we can move to a material with a higher tensile strength and with better elongation as well to achieve this lightweight design. So, but if we move to a material with a higher tensile strength, in theory, we have a good material without defects, so a perfect material, let's say, we will increase also the fatigue resistance of the material, so we can reduce the thickness of the material that we are using. But when we are using or we're addressing these different applications where we have trimming operations, serrated edges, or also perhaps we have some coatings like in press hardening materials, so we're introducing some defects in the material. So such defects can reduce and limit the fatigue resistance of the material. Then it's not that clear that the lightweight design can be addressed by only using a material with a higher tensile strength. Additionally, if you look at the fracture toughness evolution by considering increasing the tensile strength, we see that in the conventional materials, if we increase the tensile strength of the material, the fracture toughness is reduced, but not for all the materials. So, for instance, for a given yield strength, we can move to another material with another microstructure to maintain this fracture toughness or even improve it. So the aim is to use these two different properties, fracture toughness and fatigue, and see how we can use mainly the fracture toughness properties to assess which will be the fatigue resistance when we have a defect in the component. So in this case, in the Fatigue for Light project, we addressed this point by testing 3 different materials, a DP, CP, and 2 CP grades. And the main idea is to cover a wide range of mechanical properties with different tensile strength and also different microstructures to see how we can achieve this lightweight design. In this case, we evaluated the fatigue resistance of the material by testing two different conditions. On one side, we have these hourglass specimens with a poly stage. So this is the perfect condition, let's say, without defects. So and can be considered a notch specimens. And on the other side, we have this trimmed specimens, so where we have the defect here in the edge, and we can consider them as notch. So the trimmed specimens were obtained by simply sharing the material, and we obtained the well-known shared edge morphology, where we have, well, this plastic deformation, but also these small defects that we are introducing due to the fracture of the material in these operations. In this case, we trimmed the materials with the same or almost the same clearance, and we tested the fatigue behavior of these materials. In this case, we used a rapid fatigue method that we developed in the Fatigue for Light project. This method is based on to see how the fatigue damage is evolving during this fatigue test, where we are increasing the stress amplitude between these different fatigue blocks. And by using this data, we can rapidly assess the fatigue limit of the material and have an idea of what's happening or which will be the effect of these different defects in the fatigue resistance. In this case, we are always focusing in this incipient fatigue damage, in this continuum damage mechanics regime, and we are just skipping the part of fracture mechanics when we have a large crack and the crack is only propagating. So we also evaluated the fracture toughness by using the essential work of fracture. As has been explained, we can obtain the energy required to initiate the crack, but also the energy required to initiate and propagate this crack. And if we analyze the data that we obtain, the fatigue results from the rapid method, we can clearly see a difference. In this case, you can see the plastic strain. So this is the damage, let's say, that we have in the material and how it's evolving throughout the test. So is the plastic strain plotted against the maximum stress amplitude for each fatigue block. And here, by analyzing this data and using the points that belongs to this microcrack initiation and also microcrack propagation, we can easily determine the fatigue limit of the material with the different conditions. And also here we compared the results from the rapid fatigue method and also with the results obtained by the star case method, so the conventional methods, and we obtained, let's say, the same results. So here, if we plot this fatigue data for the condition without defects, so the perfect condition against the tensile strength, what we can see is what we saw at the beginning of the presentation. So if we increase the tensile strength of the material, we increase the fatigue resistance of the material. But when we have a defect, this behavior is completely different. And for some materials, we have some fatigue reduction. So for instance, for the DP600, the fatigue resistance is almost maintained, but for the other materials, it's reduced for the CP. So such fatigue reduction can be quantified by using this fatigue strength reduction factor. That is simply the relation between the fatigue resistance of the trimmed specimens against the polished ones. And this fatigue strength reduction factor is related to the damage tolerance of the material. So if we plot this data, this fatigue strength reduction factor against the fracture toughness values that we obtained with the essential work of fracture test, we can clearly see that at a given point we are achieving a kind of a plateau. So the materials that present high fracture toughness shows also a low sensitivity to the effects. So this KF factor, this fatigue strength reduction factor, is almost 1. So the fatigue resistance between the polished and the trimmed specimens is almost the same. This trend is also maintained for the energy required to initiate a crack. But why we can relate these two properties, this fatigue behavior and also the fracture toughness behavior? Well, here you have a defect that we can find in the trimmed edge. And the main point is that if we analyze which is the dimension of the cyclic plastic zone at the tip of this defect, which can be considered as a crack, this plastic zone is quite large, so is really relevant compared to the dimension of the crack. So for these materials, we can say that the small scale yielding conditions are not fulfilled. So, and if we want to explain how these small cracks behave in these materials, we have to use elastic plastic fracture mechanics approach, which one of the common and the most used is the secret J integral, which is essentially or can be equivalent to the essential worker fracture method. So, but at the end of the day, what we want to propose and what we develop as a tool is this plot, where here you can see the fatigue data for the polish stage. So this is let's say a conventional result that you can obtain from the steel makers against the fracture toughness values. So by plotting all of these data here, you can clearly see that some materials present a really good fatigue resistance, but the fracture toughness is really low. So this means that we will have a material with a good fatigue resistance, but when we have a defect there, the fatigue resistance will be completely reduced. So the main aim is try to use this graph to select the new materials to address this lightweight design. For instance, here you can see the material that Davide showed for the wheels, this DP steel, and then, for instance, the CP 800 is this one here. So this is the trend is try to use the materials with both, let's say, high fatigue resistance, but also high fracture toughness values. Now it's time for Michele. I leave the word to you.
Thank you, Sergi. So, good morning to everyone. So, in Fatigue for Light, we are working not only on the samples, so on the small pieces of steel, but we would like also characterize the component to understand if what we see at sample size can be reflected also in real part. For this reason, we took under exam a complex component that we have in our vehicle, a chassis component, safety component, that is the lower control arm. And today, such kind of component in our vehicle is done using the complex phase 800. The goal is to produce and test this kind of grade, this kind of component using the CP980. So the ones that we have seen just before, tested by Sergi. To do that, we would like to stamp the component at 3.5 millimeter for both the materials, make the bench test of the components, and after correlate virtually what we see in the physical bench test and what we see on the virtual simulation. After making the merging of these two results and having at the end the same figures, we will try to understand what will be the maximum lightweight that we can achieve using the CP980. Oh, sorry. So, to do that, we perform firstly the simulation on the CP800. Here you can see the fatigue simulation on the free edges, so in which we can have the start of the fatigue cracks, and also in the welded area. We perform as well the misuse test, that is an overload test, and this kind of experimentation is needed to validate such kind of component. And also in this case, the CP800 passed this test. And after we moved to the innovative material, so the CP980, we perform also in this test the simulation on the free edges, and we highlighted in the diagram where, and in the component where we have the critical area that we have to pay attention during the bench test. We have also modified a little bit the welding characterization in order to enhance as much as possible the fatigue performance of this area. Also in this case, the solution with the CP980 seems to work. And finally, the misuse, for which we put in correlation the system results, so the component with the surrounding components assembly together, and also the test on the spare part. This because, as you can see, the behavior that we have in the real car and in the bench is different. So we have to find a way to correlate these two behaviors. After received the good results in simulation, we moved on the making part of the project, so to realize the component. First of all, we did the stamping simulation for the two grades. At the left, you can see the CP800, for which the simulation in autoform return a completely green feedback. And at the right of this slide, you can see the simulation on the 980, for which the stamping is more complicated because the formability is lower. These return a yellow rate in autoform, but with some adjustment, we were able to stamp the component and assemble it, also making the welding of the bushing. The component that you see in this picture are done with the 980 grade, so are the ones that will be tested on the bench. On the bench, we are planning to perform the misuse, the fatigue test on the base material and on the welded area. So at the end of this characterization, we will correlate the physical test with the simulation to understand if they are aligned. And before the end of September, we will see what will be the maximum lightweight that we could achieve using such kind of material. In parallel, together with the other partners of the projects, we would like also to run some simulation about the fatigue, including new material cards. So to take in consideration the aspect of the edge cracking and the fast fatigue testing, in order to see if using such kind of a card we are more near to the reality than the ones that we are usually used in our internal process in Stellantis. So I give the appointment to the next presentation to see you the results of these projects. Thank you.
Okay, thank you very much, Sergi and Michele, again for the presentation. Okay, now we can move maybe to the next one. The next one we will see other case studies also related to the previous presentation we have seen also this morning, validating the potential of fracture toughness with the industry. This presentation also will be done by Laura Grifé, so you have met Laura before, so no introduction needed. And also Simon Jonsson, from this is a PhD student at the Division of Solid Mechanics in the Luleå University of Technology. She's working with the sheet metal characterization and simulation work to evaluate the crashworthiness of high-strength steels. So please, Laura and Simon.
Okay, thank you, David, for the presentation. Okay, so yes, as David said, we will talk about other case studies. We have seen already some cases from the open call in the project of the ToughSteel, but here we can see other cases we have been performing here at Eurecat with collaboration with other companies, as well as the potential for the application of this method of the essential work of fracture. In the application, or we are in this project disseminating this method to predict fracture toughness and edge cracking related problems, and we are willing to implement this methodology because this is a needed parameter now that we are getting higher strength steels, or we face new challenges with the edge cracking in different applications. Some of the cases where this methodology could help to improve the material properties would be in microstructural design, for example, also in edge cracking and in formability assessment. We can also see some improvements or definition in crash failure behavior. And we can also use this methodology to assess the coil quality in different materials, and also use it for material selection and in the applications that are needed in the final products. Now we will present some of industrial case studies that we have seen in the previous years. We will start first with one of the case studies in the open call in the ToughSteel project, which was with Marcegaglia. In this case, we studied 4 carbon steels with different anisotropies, and the objective for this case study with Marcegaglia was to analyze the influence of the mechanical properties on stretch flexibility of these different carbon steels. In this case, we have 2 groups of materials. One was C67 and the other C45 with different anisotropies values. And we performed the test, as we explained before, with the essential work of fracture method, with double edge notch tension specimens, and we get the fracture values as we have done for the previous results. Next, we can see here the values or the results that we got for these materials. We have separated in C67 and C45. And we can see, for example, in C65 that the values for the essential work of fracture were quite different. In this case, only changing the anisotropy of this material. In the case for lower anisotropy, the essential work of fracture value was lower than for the other case. In the material C45, we found that the results were similar, although in this case, the material with lower anisotropy showed a little higher essential work of fracture values. We also obtained the values for essential work of fracture at initiation of propagation, which is the energy needed to start the crack propagation. And we found similar tendency with the essential work of fracture results. In the plastic work, we could find that material C67 with higher anisotropy was quite higher than for the other materials. Later, we could relate these essential work of fracture parameters with the mechanical properties, and we could find some different tendencies. For the UTS, it was decreasing with the essential work of fracture. In the yield strain, it was different between the 2 materials, the tendency. The elongation was higher, mostly when increasing the increasing work of fracture. And for the anisotropy, we have like a different tendency in both materials, and for the N value, it was increasing, although it was not expected to find this correlation. Next on, we can see another case study or industrial study that we performed in the frame of the Form Planet project. In this case, we studied also two carbon steels, C45, and in this case, we had 2 different coils from the same steel grade. In this case, we found that the essential work of fracture. Well, in this case, we had these 2 coils, one presenting some cracks in the forming process, and the other was not presenting. However, the mechanical properties were similar for all of them. When we performed the test, we could find that in the load displacement curve, when testing the specimens, we could already see some difference in the behavior of the testing part. we can see here in the red arrows that for material now okay, we were finding some drops in the load during the tensile test. In this case, we examined also the fracture surface of these specimens, and we could find that the ones that were presenting these drops in the load had some fragile fracture surface points that indicated that probably in this material there were some instabilities in the material or some defects that were propagating in this fragile mode. In what we could get from this case study was when plotting the work of fracture values for both materials, one was presenting very good statistical values, and the other one was presenting more scatter in this result. This indicated in here that the quality or the material was not that good, and that the method of essential work of fracture can identify or can detect these small defects on a material. So for coil quality, it would be a good option to study. The next case study we can see here, it was in the ToughSteel iToughSheet project, and it was in collaboration with the CRF also. In this case, they were testing, or they were forming two materials, DP1000 and CP1000, and they found some cracks in the DP material. However, they performed the mechanical property tests and the forming limit curves, and they could not find any explanation to tell why the material of DP was presenting more cracks, because even the mechanical properties or the forming limit curves were better for this material than for the other one. Then we performed the whole expansion and also essential work of fracture tests, and we could find a huge difference in the essential work of fracture values for CP1000, and this could explain better why we had this behavior of fractures during cold forming in this material. So this would be another application for edge cracking prediction, the use of essential work of fracture. Finally, we can see a fourth case study that we performed in collaboration with with Gestam. And in this case, they were performing, or they were doing these tailored parts with different heat treatments along the piece. So this piece needs to behave or to resist crash impacts. So they wanted to test which would be the impact of the heat treatments along all the piece. So in this case, we performed tests with the PHS materials, 1,050, 500, sorry, with fully martensitic microstructure. And then we also got material with the heat treatment, with two different heat treatments, the one obtaining temperate martensite and ferrite, and the other only temperate martensite. When performing the essential work of fracture test, we could find that the behavior of crack propagation of these materials with the heat treatment was really improved, and was a lot better performance in crash behavior as well than the material with the initial properties. Okay, so now I leave the floor to Simon.
Thank you, Laura. I'm going to expand a little bit on that last part, on the crash worthiness and also high-speed fracture toughness using the essential work of fracture. So first, what is crash worthiness? Well, crash worthiness in the automotive industry is basically the ability of the structure to protect its occupants during an impact. And this is usually done with the crash boxes, either in the front of the car to absorb the energy when you crash into something, or to protect the passenger cage from intrusion when you're hit from the side, for example. So basically, how do we quantify crashworthiness? Well, you can use, basically I will focus on the actual compression part of the crash boxes here, and not the side impact. So when quantifying crashworthiness in these cases, you can use a crash index. And basically what it is that you crash several different crash boxes at several different crush depths, and you measure the severity of the crack for each crushing distance. And you attach a rating to it depending on the amount of cracking, as you can see here. For example, 100% is no cracks, and 75 is below 10 millimeters, and so forth. And of course, a problem with this is that generally you spot weld these crash boxes to get it stable for the folding, as you can see here. And you're generally just interested, when you're evaluating crashworthiness of a material, in the bulk material. And when you spot weld it like this, you have classic initiation sites for cracks, and it usually starts in these spot welds. So that's a problem with this method. Interestingly, Frómeta here find a good correlation between fracture toughness measured with essential worker fracture and the crashworthiness of crash boxes. As you can see here, the higher the essential worker fracture, the better energy absorption at max intrusion, and the better the crash index decreasing rate. It's basically the evolution of the crash index with the intrusion depths. So the lower the crash index decreasing rate, the better the crash resistance, you can say. So with a higher essential worker fracture, you get better crash resistance. So basically decided to investigate this with a third generation trip-aided magnetic ferrite steel grade with a ultimate tensile strength of 1180 megapascals. And the sheet thickness is 1.4 millimeters here. And I found the essential worker fracture value from Frómeta's paper here, 104 kilojoules per square meter. And also we had a hot stamping steel with the ultimate tensile. It's a boron steel grade with the ultimate tensile strength of 1000 megapascals. And I found this from our Horizon project, the Form Planet project, and we found the essential worker fracture of 186. So as you remember from the last slide there, before doing any experiments at all, we should expect the right one, the hot stamp steel, to perform better when it comes to crashworthiness than the right one, because we have a higher essential worker fracture value there. And usually you use fall tower, like drop towers, to perform this with a huge weight and several different. And you drop it from high level and crush the boxes like that. We don't have that, and usually you have a more, maybe 5 to 10 crash boxes to get a good slope or of the evolution of the crash index. We didn't have that either. We had 3 of every box. So we started to be a little bit creative. We speckled it and used the stereo high-speed cameras. So you can see I have Phantom V1610 and 2512, and tried to do a stereo DIC measurement to capture the whole deformation from start to finish, and try to identify when the cracking happens and how to measure it. And instead of drop tower, we had a Instron very high-speed machine. It's a hydraulic loading machine, and we use this for tensile testing a lot, for pulling characterized materials at high strain rates. But we can also use it in compression, which we did here, and it's able to reach speeds of 20 meters per second. So doing this, you can of course capture video and identify when cracks happen, or when spot weld fractures. We're generally not interested in spot weld fractures because we can't really trust the material in those spots. And of course we have the intrusion depths and the loading histories here. And also we have some strain field here because we want to validate this with a finite element model. I won't show that simulation here, but we wanted to do that as well. So we tried to get the facets field of that as well. So we can identify the cracks when they initiate and how they propagate this in the end. Let's see. So by doing this, of course, we get the usual information. You get the force intrusion, force crush curves, and we can integrate them to get the energy absorption as a function of the crush depth. And as you can see for the TBF material here, we have quite scattered values there and quite consistent values for the hot stamping crash boxes there. And how come it is like this? Well, cracking, right? For the TBF material, we could see quite severe cracking in some areas there. And for the hot stamping steel, or a lot less cracking. And we could have seen this from the beginning because we saw the essential work of fracture values, right? It was higher for the right material than the left material. So we could expect that there should be less cracking and better crash resistance. And we can see that here. And a lot of the cracking for the hot stamping steel there was like under the folds, hiding in the folds there. So it was a much harder dismay with the cameras, so it's hard to see them. So we had to be a little bit creative to backtrack from the final deformation and see when we had blowouts and stuff to measure the cracks or estimate the cracks. It's a rough estimation. But basically what we received is the crash index decreasing rate here. And it was easier for the TBF material because we could see the cracks and we could measure them pretty well. And we can see that the crash index decreasing rate, it was a little bit higher than for the hot stamping grade. And I know the linear fit here is a stretch, but it was the best we could do. But the trend is clear. We can see that, as we could expect from the essential work of fracture values as well, that the crash resistance is better for the right one, the hot stamping steel. And yeah, it correlates well with the essential work of fracture. So just for curiosity, I put in the published result from Frómeta here. And if we put in the essential work of fracture values here, this is what we could expect from this graph. But of course, when we received different values, a lot higher energy absorption and lower crash index decreasing rate. So what's going on? Is it flawed? Well, hardly, right? There's explanation for it. First of all, this identifying the crash index or crash resistance using crash boxes is highly geometry dependent. And the ones they used in this study, they had a different test setup, different crash box geometry, different technicians than I did. And so, of course, the results are going to be different. And that's a problem with this method, of course, when you do crash index, crash worthiness evaluation with crash boxes. It's generally just valid for that specific experiment. We can't really extend it, and it makes it very hard to compare between materials, between researchers. So that's one thing. And also, as we saw with the linear fit there, crash index reduction rate is really hard to measure. It's very dependent on the technician and how you measure it and so forth. But furthermore, of course, it's been shown by Frómeta and Golling here as well, or Golling or Frómeta, that essential work of fracture is highly strain rate dependent. So if we have, we are always almost crushing these boxes with 20 meters per second. So locally, the strain rates are over 1,000 in these crash boxes. So we have incredibly high strain rates. And essential work of fracture increases with strain rate, as has been published before. So I decided to investigate that as well, using the essential work of fracture at high speed. It's been done by Golling before, but I tried to do it for one of the materials here. I just tested the TBF material. And the crosshead speed is 0.5 meter per second, and it can be compared with the published results when they tested with 1 millimeter per minute. So this is 30,000 times faster. But otherwise, the methodology is the same. It's been described by Laura before, so I won't go into detail. But you do the same methodology, and you receive this. And you can see that the essential work of fracture value there is significantly higher than 104 that we got from the published paper. Yeah, as you can see there. And it's something we can see from the published results for another TBF grade as well. It's not the same steel, but you can see that the essential work of fracture is significantly harder with the increased strain rate. So this, of course, makes it very important to take into account, for example, if you want to use it in modeling, in crash, that we need to take the strain rate into account. So basically, it's a summary conclusion. One great thing with the essential work of fracture methodology is it's simple. We can test it in the lab. It's straightforward. We can reproduce it. And it's geometry independent. So it's really great if you want to compare crashworthiness of materials between researchers at different research institutes. And also, EVF increases the highest strain rate. It means that if EVF should be considered in modeling, for example, the value measured at high strain rate should be considered. So basically, that was what we had. Thank you so much.
Okay, thank you. Thank you very much, Simon and Laura, for also this interesting presentation and see other potential applications, not only in forming, but also how to relate to crashworthiness. Now, so it is the time for the last presentation of this first session. So in this one, we will conclude. And as I said before, after this presentation, we will have some minutes for questions and answers. So please feel free to make your questions, write it in the chat, or hear from the audience, as we did in the previous session. You can raise your hand and ask directly to the speakers. Okay, now, as I said, we can move to the final presentation of today, which is called Fracture Toughness Test to Improve Material Selection, Example of Application at Cell Laboratories. These presentations will be done by Noemi Rodriguez. Noemi is the responsible of the Mechanical Department of Materials Technology in SEAT. So she has been involved since 2012 in the Quality Department in SEAT, and she always works related to the mechanical, corrosion, and metallic materials. So please, Noemi, wherever you want.
Well, thank you, David, for the introduction. I will explain another case study, okay, with application on fracture toughness. And then I will explain a little bit what is our department in materials technology and innovation. And then Laura will join me to explain a little bit more in detail the results obtained in the fracture toughness methodology, and then some conclusions. No, okay. As I said, I am the responsible for el metallic and corrosion and also electric laboratory in materials technology and innovation department. This department belongs to corporate quality in SEAT, and we are a group of 22 employees, most of them chemical degree and also materials engineering and some electronic engineering also. We have two main groups, one for electric functions, BodyShop and Powertrain, and another for polymers and elastomers. And then we have two cross groups, mainly for innovation and also for technical requirements and new projects. We are the reference of materials for all the companies, SEAT, Cupra, and also for micromobility and new mobilities items. For that, our responsibilities go through all the life cycle of the vehicle, from the concept of the vehicles, in the definition of the materials, new processes related to materials, also in the development, in the launching, assuring that the process and the suppliers has the capability to do all the parts, and also we are present in the serial part. Okay. As I said, we are responsible for all the brands, SEAT, Cupra, and also micromobility. Our main functions are the feasibility, development, and assurance of the materials in all of and also coatings in all of this cycle. We are also competitors in failure analysis, and we are also responsible for corrosion and weathering tests in the whole vehicle in the serial phase. As we know, our customers are demanding new trends. They are really worried about new sustainability, economic circular economy, sorry, and also animal-free concepts. Okay, so we have to take care about this, and we are really focusing on what our customers are expecting from us. And for this reason, we are transformation as a department, and we have new roles, and we are getting a lot in new innovation process and concept. And for that reason, and I take the benefit to be here today, we ask for our technological partners, suppliers, that we have to work together to give this response to our customers. Okay, for this reason, it's important for us to collaborate with really expert people in technological centers, in technological partners, to give the customers these new concepts. Okay, we are also improving and a lot in electrical laboratory. We are going to have in almost 2 years an electrical vehicle produced in Martorell. And also a very important point that we are going to use is in this vehicle also is recycled material. Okay, just with this brief introduction, I will go directly to the case study, the analysis of the problem that we had. The part that we were studying is the cross beam, that it means uses the dissipation of the cross energy. In this case, this part is from the SEAT Ibiza and Arona. Okay. The material used for this part is a dual phase due to its high strength and good formability. Okay. And the production people call us or ask us for a help because they have been many problems due to cracking. Okay, this is an example in the forming process. How is the piece? First of all, in one of the operations during the stamping process, some wrinkles appears in the pieces, and after that, in the next operation, some cracks appear in the edge of the piece. Okay, we know that this material, the dual phase material, the adjustment of the tool is really relevant for that. So the first thing that we ask our colleagues in production, please take care about the adjustment, the maintenance of the tool, and it was done. And they told us that they have found many differences between many coils. So with the same adjustment of the material, of the tool, sorry, the behavior was many different between one coil from other coil. For that reason, we start to analyze the material in our facility in terms of mechanical properties. No? We have seen in many of the examples that we have seen today, we didn't find any difference in the material, in the mechanical properties. All of the coil that we were analyzing were under the specification in terms of mechanical properties. And we did some trials to improve the behavior. The improvement of the tool, as I said, was done, was not more to do. We increased also the oil content on the piece to avoid this cracking, but it was not successful. And something that was successful was to sort the coils by the elongation value. Okay, we found that the coils with more than 17% of elongation, the behavior was really good, But it was not possible for the supplier to give us always this elongation because it was not a robust measure, so we decided not to implement. It was not possible. And then we changed for another quality of material, the DH quality of material. Finally, this was the more efficient measurement that is now applied in the serial, but we as a materials department thought, well, okay, now it's solved, but we have to find a little bit more on this and try to analyze. For this, we contact Eurecat to find some requirement to predict this crack initiation and the fracture toughness, and we knew about this new method, and we tried a kind of study with them. And Laura, if you want.
Thank you, Noemi. So yes, she said with this problem that they presented, we wanted to try the essential work of fracture method, but we wanted also to give them the opportunity to do the tests. Okay, so yeah, we decided we wanted to do the essential work of fracture method, which is a simple mathematical method. However, the specimen preparation is quite difficult because we need to propagate cracks, and this takes times, and it's complicated to control all these parameters. Then what we proposed them was to use a new tool that we have developed here in Eurecat, which is a method to create sharp notches in a specimen in just a few moments. Okay. One critical aspect to measure fracture toughness is that the radius of the crack tip. So it needs to be very small so that it doesn't depend on the radius of this crack tip. So with this method, we can perform this fast and reliable method to measure fracture toughness. We can see here just a description of the tool and how it works. Mainly, one of the important things is that we can set this tool to any universal testing machine, and we can create these two sharp notches symmetrical in just 1 minute. When we were saying before, for example, that to propagate a crack, it takes 1 hour or 2 for one specimen if it works well. So we can decrease this time for 1 minute, 90 minutes to only 1 minute for specimen. So to create a range of ligament lengths, which is what we need to calculate the essential work of fracture, we will take only 10 minutes to create these cracks, while it would take more than 1 day to do it with fatigue pre-cracks. The system of this tool is that we have a bevel punch that can, with a shearing process, it can create these two symmetrical cracks. And we have a radius of the notch of about 2 microns. For fatigue pre-cracks, usually it's 0.1 microns, but we can adapt it, or we can trust the values for the essential work of fracture. Then we can do the test as usual with the tensile machine of the cracked specimen. Then with all the experimental part, we send the tool to, or we gave the tool to SEAT. They installed it to their facilities, so they started testing all the materials. With this, they had to test, or they tested 11 coils of material, which was quite a lot of material, so it was not possible to do it with the fatigue pre-cracks and get fast results. So it needed something to be implementable to the industry. So we got these 11 coils, and here we can find the results that we obtained for the essential work of fracture values. We separated here in blue the material DP, and in orange the results for material DH. And we already saw a tendency with better results for the material DH. So we already knew with this parameter that this material would be better than the DP for edge cracking or cracking problems. Also, what we could find is that some DPs, for example, had good fracture toughness values, that maybe these ones could be used to fabricate the pieces without any cracking problems, and it would be a good way to choose between the DP materials, the best ones to use in the process. We also compared the mechanical properties of all these coils with the essential work of fracture, and we could see, for example, for the maximum resistance, that the values were similar for all of them. However, the essential work of fracture was better for usually the DP materials. In the elongation, for example, we could find that better elongation for the materials did not always mean that the essential work of fracture was better too. So it was a parameter that should be taken with care. Also with the maximum resistance, we found the same, that the values were similar for all the coils. However, for the essential work of fracture, it was better in the DH materials. Finally, we wanted to even simplify more this process. In this case, we used a range of 8 or 10 specimens for each material, but we want a faster method and that can be applicable easily to the industry. Then we decided to use only one ligament length to at least classify the different coils and its fracture behavior. Then what we use is this only ligament length of 8 millimeters, and we measured different parameters. One was the work of fracture, which is this area under the load displacement curves. We also checked the maximum load of these curves and the displacement at fracture. And we could see here in the results that the materials were escalating similar to what we found with the complete essential work of fracture method. So this could be a new step that we could implement with the essential work of fracture and how to predict edge cracking or fracture-related problems. Finally, just some challenges and aspects to consider. That when we did the testing, we found some issues that can be improved or that can be taken into account. One was the measurement of the ligament length, for example. This is a critical measurement to obtain the final fracture toughness results. So this is something that needs to be improved or taken with care. We also find that the utilization of only one single ligament length instead of a range of ligament lengths can be a good option for material classification and fast in the industry. And also we need to inspect better the correlation with the actual behavior of this material in the real production. So these are new challenges that we can face with this project, and we hope to see them. So I leave to Noemi for the final conclusions.
Yeah, just a final conclusions for this study. Okay, we knew that the DH quality is better behavior in production, and we have found that with the fracture toughness is also seen that the results are better. But with DP grades, we see that some coils exhibit also good behavior and also good results in fracture toughness. So maybe this value is a good value or a good option to have in the specification in order to sort and to avoid these kind of problems. And we have seen also that this method, as Laura said, is a good method for production, to install in production line. For the people that work in there in production, it is not necessary. We have experience that is an easy way to analyze just in a few minutes, and it's not necessary. One is a judge, it's not necessary to have a high knowledge in materials technology, for example. And the next step that we are going to do, we have regularly a meeting in the, as you said, in the concern, so with Audi, Skoda, different Volkswagen plants. We are going to present the results there because we think it is very interesting, and we want to push in the group to analyze better this behavior and try to introduce in our standards, a little in our VB standards. And study the possibility to as I said, to incorporate this method in the standards of the group. And that's it for our side. Do you have any questions?
Thank you. Okay, thank you very much, Noemi and Laura, also for the presentation. Now, as I said, we will have some time for make questions to the speakers now. I think, again, I would like to invite the speakers to the table. I hope there's room for everyone. Okay, there's any question from the audience?
Thank you. So a question for Simon. It is regarding the strain rate differences when you try to compare the behavior in crash test. In fact, did you test different strain rates, or you have only two values? And which are the value, if you can remind me, the difference in terms of value for the strain rates?
So I tested one of the materials at one strain rate, and it was 0.5 meters per second in crosshair speed. So the local ductility, local fracture, the strain rate at close to fracture was, capped at 1,000, probably higher in the local by the crack tip. So it's really high, close to fracture, when it starts to propagate.
And the term of the normal strain rate.
For the global,
yes.
Or I'm not sure. Have to check.
Okay.
Check, yeah.
Is it written in your presentation or not?
No, I don't think it is. But I can.
We can exchange by email later.
Yeah.
Okay.
We can discuss
Thank
later.
you.
Yeah.
Thank you.
Yeah, good morning. The question is for Noemi. You said that you are going to present the idea to extend the test in the whole group of Volkswagen and SEAT. I know that my question is a bit risky, because it's not, probably the answer is not easy. But usually, how long does it take if they accept the idea to deploy the test to the whole group? And, well, I don't know, which are your feelings about that?
Well, my feeling, I suppose you can imagine, it's long. But I can see that something is changing a little bit in the whole group, because they are also waiting that the other brands, SEAT, Skoda, will join with more new ideas, new analysis, and they are fixing a lot in our way to work, because we are more agile, we are not as a big institution. So I think they are considering a lot of our ideas. So in this meeting it's working properly. Okay, we stay in contact. So I think they will consider for sure, but the time, well, we will see.
Maybe a question for the Eurecat researchers. Laura, for example, I saw in one presentation that there is this sudden drop of the load during the EVF tests, and you related that to some material quality problems. For example, have you seen that behavior earlier during the tests? I'm just thinking that how kind of often you see this kind of load drop and maybe some quality problems.
Yeah, we find, well, we have found, we find it sometimes. It depends on the material, but in some cases we can find these problems. It's not the most common one maybe to find in this test, but yeah, from time to time we can find them, not too often.
Yeah. Usually also when we have found this more often, this kind of problems or this kind of behaviors, especially with experimental materials, where they are the development stage. But that's a good way, of course, of detecting all these kinds of different material processing, different microstructure, different defects, precipitation, clustering, all those kind of defects that can affect very locally this fracture behavior. But this is where we have seen more often. But usually in this kind of commercial or like commercially available and so on, it's not so useful to see that kind of behavior.
My question is a consequence of the previous question, which was carried out to Noemi. More than a question, is an appreciation, because one thing is that the Volkswagen Group decided to implement a new property, but this new property has also to be implemented in the steelmaking plants. I mean, the steelmaking should include a new property in their, let's say, property chart for its single quality or a very specific quality, because we have seen in many of the slides, apparently the same steel doesn't perform the same. So there should be a kind of division between the same quality to, let's say, the CP1001, CP1002, because they perform different based on the steel toughness. Because otherwise, even the request is made by the steelmaking, it would take quite a long time to be implemented by the steelmakers. Yeah. So it needs to be somehow synchronized.
Exactly. I think we have to work together, work in group, but until the OEMs doesn't ask for that value, they can, the steelmakers can work in parallel, but I think until we are not going to ask in the standards, we cannot ask them to do the products like that. So I think we have to go in parallel and work together. Yeah. And in this group, as I said, most of the times we are inviting steel makers. They are showing new processes, new products, and we are working a lot together with them. Yeah.
Sorry, I am very bad for remember the names. It's a question for you. Yeah. Sorry. You told us before that you are using a coating to reduce the stress of the piece. What kind of coating?
It's a good question. I know the word in Spanish is nitrurado. Sorry, because I don't know the word in English, but it's that kind of coating for the tool. And the improvement, the results are amazing. We are very satisfied.
Juanjo, thanks for asking the same I'm going to ask. No, this is an interesting point. Maybe because it's difficult. Noemi, you tell it's difficult. Now we have some steelmakers here, some others online, and I listen carefully to that. I know it's a long process, but we started many years ago, so we are on the way, I think. Maybe a solution in between is to adjust production parameters according to the properties we have, because this can be a good option. Coatings, maybe another coating can be also better. You saw that the lubricants are not giving much benefit, then coatings can be another strategy. Also, playing the geometry, as you mentioned, it's also a good strategy. So but you should know if the materials that you're going to form are prone to have crack or not. So if you know from the beginning, that can be interesting. Do you think you can play a little bit with this?
I'm not sure if I will answer your question exactly, but I would like to give my point of view. Here, the constructor of cars like SEAT and the main supplier of raw material like SSAB are not working together. Yeah? Yeah. Don't laugh. This is my life. This is my life. I am in the middle. So, Benteler,
yes, you are in the middle.
Benteler only can choose or discuss the steel that we will use in the lifetime of the project at the beginning, in the development phase. And the plant who will manufacture the parts are not involved. So after that, if we have a problem with any kind of material, for example, 3800, or we have another problems with FB 780, we have to do our I+D work without discuss the material. We can change it. And that's a very big problem.
Now we have a new tool. I hope I can help in this. Noemi, please. I know that now that the laboratory at SEAT, they are really active in doing this innovation and doing research. Maybe it can be a nice starting point for testing with some steel makers, some grades, just at your scale, because you have a lot of knowledge, and then start proving this.
We have just talked before about that, because we are, as I said, we are really, well, in the company, we are really focusing on new concepts with sustainable concepts, circular economy, these kind of things. As I heard this material, this fossil-free material, I said we have to talk about that because it's really important. And as I said, we cannot do it alone, in SEAT or Cupra. We need our technological partners within central technological center to help us and try to work more together, and you said, for sure we can improve, but I think it's the only way to give the customer the good solution for that. We will do it.
And at the end, we are at Europe level, so I think we should push automotive in Europe a lot.
Exactly.
We have to help each other. If I can have another question, this is for Davide, because you show another kind of stuff about fatigue. It's really interesting, the wheel sector. You show that if I get it right, you show that the materials with a higher toughness explain well the behavior at high fatigue loads and also at low fatigue loads, or only at high? I didn't get the picture right.
No, both.
Both.
Both cases are well explained, well demonstrated. It's not really a really low load, so a very huge number of cycles, because the high load, the number of cycles are around, if I remember well, 200,000 cycles, and low load is around 400 or 500,000 cycles.
That would be really interesting to see what happens at the really, really low loads, I mean, close to the fatigue limit. Because probably what happens is that what you feel or what you test is the resistance of the material for a crack propagation, and the fatigue, that even if not the same, that monotonic stuff can be related. So I think this is a good approach to have. Do you have tested higher number of cycles, close to 1 million? Do you understand that? I refer to millions.
We tested on that type of range because it's the range in which the OEM required to validate the wheel. So typically the validation of a wheel is in a range between 100,000 till 600,000 cycles. They don't require to go.
Then that's why it could be a good tool as well. Okay, grazie. And if possible, the last one, I promise, because we discussed yesterday, there's a lot of things happening in sustainability. And you suggest a solution, an interesting solution for chassis weight reduction. What do you think about the life cycle analysis that is done in the sector, how we can improve material selection from that point of view?
Yeah, as I explained before by the colleagues of SEAT, the sustainability and the recyclability of the material is very important, and will be in the future key factors in order to select not only the material to be used, but also the suppliers. So we are looking as a Stellantis steel maker, but we can enlarge to not steel maker, sorry, OEMs. But we enlarge to all the OEMs in Europe and also in North America that we would like to implement in the new vehicles, in the new platform, in new top hat, materials that are more and more sustainable. So that means low CO2 products, or even the higher recycling content. The basic idea is to create the so-called closed loop. So after the stamping, we know very well that we are producing scrap because we have, especially in conforming, extra material to be used to make the part. The concept is to take this scrap, send back to the steel maker, and make again the steel for us. In this way, we can create this circularity of the material, and we can also preserve the quality of the steel that we are using. Because as you well know, the quality of automotive is very high. And we have seen in the presentation before that each single minimum problem causes the effect on the production. So we need to keep the quality high, and we need to close the loop with the steel makers.
Interesting times.
Laura, you commented upon the influence of the ligament length for testing. What are the actual implications of the different ligament length in the actual behavior when stamping in practice? Would it be better to choose a test with lower ligament or with a larger one? What would be more reasonable to be comparable with the actual life of the processing of such a piece of steel?
Yeah, I think we have seen that for the experimental test we have, ligament length of 8 millimeters describes well the fracture toughness. There's also a range of ligament length that can be applied for each material. There are some restrictions for the plastic radius formed in the material. So we can get to these restrictions in the material. They are related to the yield strength of the material, right? So I think we have to stick or to stay in the limits of each material according to its properties and how the deformation behaves around the crack edge. So I think that's why we choose these materials. And it's not that the length should be the same as the one we have in the part. The cracks at the end, it's just the radius of the crack which matters, and how the deformation happens in front of this crack. Okay.
Okay. Well, we are running out of time, but we have time for also other questions that we have from the audience online. The first one I think is also related to Laura and Noemi. Is there a large variation over the coil length and width? On which position did you do this measurement?
I think we did in different positions, no, of the coil. Yeah, no. We normally perform in the 10% of the beginning of the coil. This is the normal sample that our supplier that cuts the material gives us.
Then we have a supplier who cuts all the coils. Then they take a sample at 10% of the coil. Every sample is in the same place.
Okay, thank you. Okay, another question for Noemi and Laura. You showed that this is a complex one. You showed that the DH grade behaves better with regard to crack initiation than the dual phase grade. So do you have some explanation for this better behavior? What is the role of the microstructural components?
Yeah, we have not shown, but we have tried to understand what happens in the macrostructure. We have not found any big difference in the macrostructure of both materials. And as we have talked with our suppliers, the big difference is in the proportion of the ferrite martensite in the microstructure is something about cooling transformation.
Okay, thank you. Okay, and one last question. So the first speaker, it refers to Miguel, mentioned that the use of a scrap had an influence on the fracture toughness. Do you know what chemical element levels were elevated in the material that was made using scrap?
No. The answer is no. We have tried. No. We have made some study of the chemical analysis from several coils. I don't know how many coils, like 1,000, and we don't know which chemical is affecting. So it is totally random. it would be another effect, but we don't know. That's the problem.
Okay, well, thank you very much. Thank you again, all the speakers. So we can get an applause for all the speakers again.